So, hello everyone, we should start the last session of this workshop. So our first speaker is Manimala Mitra and she is online. She will be telling us about the extended Higgs sector in single-triplet fermionic model for dark matter and neutrino mass. Manimala, you have 20 minutes and let's see how the time goes and I will remind you accordingly.
Yeah, sure. So I can start now. Okay. So first of all, thanks to the organizers for giving me this opportunity to give this talk. And it's really a very pity. I mean, I could not attend this in person, although everything was sort of like said that yesterday I will take the flight. But anyway, something we cannot change. So I'm going to talk about extended Higgs sector in singlet-triplet fermionic model for dark matter and neutrino mass. Although I mean, almost there is nothing that I will be actually speaking here about neutrino mass, as you will see. This is very much related to this work that we published a couple of years back with Genevieve Rohini and my students and some of the other collaborators. So I don't need to explain this in detail. We know that this is the measurement from Planck about the dark matter relic density, and some of the very important questions at the moment is about the dark matter production. So whether dark matter is a weakly interacting massive particle or is a feebly interacting massive particle, and some of the other production mechanisms such as conversion driven freeze out or the number changing processes in dark sector. So they are getting much more importance these days. So just to set the context, so for the weakly interacting massive particle, we know that at the very early epoch, dark matter was in thermal equilibrium with the rest of the bath particles. So following this trajectory. And then as universe expanded, at some point it basically decoupled and this is the thermal abundance of the dark matter, the relic abundance. If the dark matter is a feebly interacting massive particle, then the dark matter was never in thermal equilibrium with the bath particles. So it was produced from decay or annihilation of the thermal bath particles, right? So at the very early epoch, it has very nominal abundance, or in fact, it can also have zero abundance. And as the universe expanded, it was produced from the decay and annihilation of other particles. So this is the relic abundance. So now I will be discussing about this particular model. So this is an interesting model because of the certain things that you will see as I proceed in the next slides. So to discuss this model, we have a SU2 triplet fermionic field. In fact, we have actually 3 generations. So this is basically rho. And then SU2 singlet and all the standard model gauge singlet fermionic field, which is N prime. So rho has hypercharge 0. It's a SU2 triplet. Now this rho 3, so among the 3 generations, the third component, rho 3 and N prime, they are basically the dark sector particles. Okay, so and the moment you try to write an interaction terms between rho 3 and N prime, and if you stick to the renormalizable Lagrangian, then you will need this Higgs field. It's a SU2 triplet field with hypercharge 0. So delta 0 is required just to complete this Lagrangian. Okay. Now if we expand this delta, so this delta has a 0th component, electromagnetic charge neutral component, and then it has delta plus and delta minus. And these rho fields, the triplet fields, they have rho 0, the neutral component, and rho plus and rho minus electromagnetic charge component. So these are the fermion fields. The rhos are the fermion fields. N prime, this is the fermion field, and delta is a scalar field. And if you impose a Z2 symmetry, then you can show that this dark matter. So here the idea is that the combination of rho 3 and N prime, they can be the dark matter candidate. So with a Z2 symmetry, you can always stabilize that. This delta acquires an induced vacuum expectation value, where this vacuum expectation value, which we denote as V delta, this is proportional to this electroweak wave square divided by the bare mass square of this delta field. times this strength, this coupling mu, where mu governs the interaction between the delta field and the standard model Higgs field. Okay. So altogether, this other two generation, rho 1 and 2, they basically, they are irrelevant here because so they sort of like are decoupled from this sector, this dark sector. So they participate in neutrino mass generation, rho 1 and 2, and rho 3 and n prime, they are the dark sector particles. So now this model has this delta field. So this brings up interesting phenomenology in the scalar sector. So the neutral component, this delta 0 mixes with the standard model Higgs field, and this H1 is the standard model, the 125 GeV standard model Higgs, and this H2 is a BSM Higgs, CP even neutral BSM Higgs. And not only this, and their mixing is denoted as sin alpha. And not only this, this delta has a plus minus component that mixes with this, the charge component of the SM Higgs doublet. And this G plus minus is a goldstone, charged goldstone, and it has a charged physical Higgs, which is H plus minus. And where this mixing has a very simple expression. So mixing is nothing but the ratio of this triplet wave divided by the electroweak vacuum expectation value. And similarly, the mass of the charged Higgs is also has a very simple form. So this is just this interaction strength mu times electroweak waves divided by this combination of these mixing parameters. So just for simplicity, we have considered a scenario where the neutral Higgs mixing is equal to this charged Higgs mixing. Although one can always deviate this condition and you will get sort of like similar kind of phenomenology. Now in the dark matter part, the third component, rho 3, that has an electromagnetic charge neutral part, that basically mixes with this n prime, with this mixing parameter beta. So, and it gives two eigenstate, one is rho and n. And this, this rho 3 and n prime, so remember they basically interacts with this Higgs field, the SU2 triplet Higgs field delta with this interaction coupling y rho delta. So one can express y rho delta in terms of the mass splitting of this rho and n field times this sine 2 beta. So this is this angle divided by 2 v delta. So we are working in a regime where we are basically introducing a very small coupling, this y rho delta of the order of 10 to the power minus 10 and 10 to the power minus 12, and we want to see what is the effect of this in the dark matter phenomenology. And that basically implies that this beta is practically 0. So the scenario is that the n is practically, it's a singlet field, and rho, this rho is practically a triplet state. So with this, there are only 5 parameters in this model. One is m rho, mass of this rho. Then the second is mass of this n. Third is mass of the BSM Higgs. Then this Yukawa coupling y rho delta, which is extremely crucial for the dark matter study, and the mixing angle between the CP even Higgs. Now, about the dark matter phenomenology, if we are sticking to the fact that we want a fermion to be dark matter, so either rho or n, they can be dark matter candidate depending on their mass hierarchy. So altogether, so this flow chart sort of like summarizes the importance of different production processes. So if rho is the dark matter, and that happens if the mass of rho is less than the mass of the n, then there are certain processes, they becomes important. And if n is the dark matter candidate, then that happens when the mass of n is less than mass of the rho. But there is a very crucial difference between these two. So remember, rho is a SU2 triplet. So therefore, what happens that always the rho to bath particle is possible. On the other hand, so that is basically a thermal dark matter candidate. So it will be a WIMP dark matter candidate. On the other hand, if n is the dark matter candidate, and because we are working in this regime, this kind of very small coupling, so what happens that n is actually non-thermal candidate, so it's basically a WIMP dark matter candidate. But the importance part is that even this rho is a WIMP dark matter candidate, as I will show in the subsequent slides, that the production of rho from the late decay of this N that gives significant contribution in the relic density. So the idea is that N is a non-thermal particle. It's produced from the decay of this BSM Higgs H2. So H2 can decay to N rho. That will basically build up the abundance of N. And then the further late decay of N can give substantial contribution to the relic density of rho. On the other hand, the other possibilities are also there. So this is called fusion dominated, where the bath particle gives rise to N production, and then the decay of N going to rho H2, it gives substantial contribution to the relic abundance. In the case where N is the dark matter candidate, because N is a FIMP dark matter candidate, so primarily it's produced from the decay of this BSM Higgs H2. So H2 can decay to N rho. Although the late decay of rho to NH1, that gives again substantial contribution to the relic abundance. And the fourth one is where in addition to these kind of decay modes, rho going to NH2, the annihilation contribution, so this is the direct annihilation of bath particle to rho N, that gives a significant amount of contribution in the abundance of N. So this, with this kind of coupling in mind, this sort of like summarize the different production process and the interplay of the different scenario where rho is a dark matter candidate versus N is the dark matter candidate. Now, before I move into detail, because rho is a SU2 triplet field, so rho is a SU2 triplet field and it's a thermal dark matter. So certain constraints we need to keep in mind. The first constraint is, of course, the collider constraint. So rho contains rho plus minus and rho 0. And rho plus minus and rho 0 and rho plus minus decays to rho 0 and pion. So what happens that basically this pion is very soft. So and therefore this will manifest itself as disappearing track signal. So there is a bound around 580 GeV from Atlas searches. The second one is applicable if the dark matter, rho is a dark matter. So then direct and indirect constraints one is to take into account. So the direct constraint is rho n to rho n, but in this model you don't get a tree level contribution, but you can have loop level contribution mediated by the, for example, this is one of the diagram, W mediated loop and two loop gluon contribution. And this is the prediction if you consider these contributions together. So direct contribution, and these are the experimental constraints. So all of this part is actually ruled out, but this is our theoretical prediction. So the direct detection actually does not impose any significant constraints for this scenario where rho is the dark matter. This is the indirect detection constraint. So this is here the rho to W plus W minus has been shown. So this is magic plus Fermilat, this part, and this is again our theoretical prediction. So one can obtain a very relaxed kind of bound around 380 GeV. So altogether the collider constraint is very strong. So now I consider the different scenarios. The first scenario is where the dark matter is a rho candidate, rho is a dark matter. And we consider a mass range which is more than 580 GeV or 600 GeV onwards. So that basically implies that if we want to satisfy the proper relic abundance, we need this additional contribution, because we know that for a triplet field, for example, this kind of diagram becomes very important, and unless and until M rho is around 2.4 TeV, one will have underabundant dark matter. So that gives a very strong motivation that if you are considered less than 1 TeV mass range for the dark matter, the rho dark matter, so let's say from 600 GeV or 700 GeV to 1 TeV or 1.5 TeV, then it will give underabundant contribution. And this additional contribution, so for example, H2 going to rho n, and n has a late decay giving rise to rho H1, it can compensate the underabundance. So to solve, to find out the relic abundance, one needs to solve the Boltzmann equation. So this is the Boltzmann equation for rho. But for n, one also needs to solve for the abundance of n, because n abundance enters in the Boltzmann equation for rho. But because n is non-thermal, so therefore we do not directly compute yn. Rather, we compute the distribution function of Fn. Okay, so all these technicalities have been explained well in our paper, and this is very well known also. So this is a plot of this abundance of rho and abundance of N versus the mass of rho by temperature. This part, so this is the standard freeze out part for rho abundance, and we see that it gives under abundant dark matter for rho, but this additional contribution, so these are the abundance of N from H2 decay and which saturates, and then at some point this N basically decays down to rho, and therefore this is the non-thermal contribution. This is the late decay contribution. So together this freeze out contribution and late decay contribution, you can satisfy the relic density. So we have added some of the parameters, the relevant parameters in this kind of range, and in this plot we show the MH2 versus Y rho delta, and the color bar represents the variation of Mn. So this part follows very much linear kind of relation, because when you calculate the abundance of N, then you will see that for a very heavy MH2, it basically goes as Y rho delta square divided by MH2, and therefore as MH2 increases, one also needs to increase Y rho delta so that the relic density is satisfied. But this is the part where there are some additional phase space suppression is present from the calculation of this relic abundance of N. Here what is happening, that as MH2 is increased, then we can see that is sort of like Y rho delta sort of like is falling down. Now the second part is where rho is not a dark matter, N is a dark matter. Now remember, N is a freezing film dark matter. So that basically implies that it was never in thermal equilibrium. So here the primary production modes are H2 or H plus minus to rho N. This is the thermal production mode. And then there is the additional contribution from rho decay. So rho going to NH1, it gives the late decay contribution. So one can write down the late decay contribution. This is the omega N NTF phi. So that is non-thermal fission contribution. Is proportional to mass of N divided by mass of rho times the abundance of this initial particle, which is rho, at the time of freeze out. So altogether there are two contributions. One is the fission contribution and the other is the non-thermal fission contribution. And here also one can see this is the thermal fission part and this is the non-thermal fission part, and together one can satisfy the relic density. Now in these two scenarios, because this kind of decay H2 to rho N is open, and because we consider that a heavy rho more than 600 GeV at least, so therefore H2 has to be heavy. So H2 is at least has to be few TeV to satisfy the relic abundance. So I think this part, this I will skip. If someone is interested, I can get back to this. Now the other scenarios are possible where one can work with a much lighter H2, and here the trick is that we want H2 to rho N is kinematically forbidden. Rather, some of the other modes can be very important. So for example, one is the fusion dominated scenario where this kind of mode 2-1 and 1-2 process can dominate the relic abundance. So this is particularly this diagram. So here what is happening, that the bath particle is producing N, and then N can decay, N is produced on shell, and then N can decay to again rho H12. Here we consider rho is the dark matter candidate. And the second scenario is where N is the dark matter candidate, then one can show that some of the other annihilation contributions, they can be very important. So now for the first part where rho is the dark matter particle, then as I have explained before in the previous slide, that this is one of the main contributions. So rho and H, BSM Higgs, it can produce N, and then N can further decay to rho and this H1. And in this plot, what I am showing the mass of the N, which is not a dark matter, but the next to lightest dot particle, NLOP. And in the y-axis is the Y rho delta, which is the Yukawa coupling. So Yuka coupling is important because it enters in this vertex. So the end production very much depends on this Yuka coupling. And in the color bar is the mass of the heavy Higgs. So contrary to the previous scenario, what we can see that if for the heavy Higgs mass as light as let's say 200 GeV or 400 GeV, so all of these points satisfies relic density. So these blue points, for example, 200 GeV, or the cyan points are 400 GeV. So we can see that for this kind of BSM Higgs mass, which is accessible at LHC, one can satisfy the relic density. And the other scenario is where N is the dark matter candidate, and if N is the dark matter candidate, then there are two production modes. One is the decay contribution of rho, so rho can again decay to NH2, but also substantial annihilation contribution. So the bath particle AB, so AB can be all of this, can directly gives rise to rho in kind of production. So here in the left side, what I am plotting, this is a mass of the BSM Higgs versus mass of this rho, which is NLOP in this case. And these different color points, so they basically represents the contribution from these decay. So for example, these are the points where the decay contribution is roughly 70 to 100%. These blue points is the point where the decay contribution is roughly 60 to 70%. And then these green points where the decay contribution is less than 60%. And all of these red points are where the decay contribution is less than 50%. So that basically implies that the annihilation contribution there is significantly large. All this lower part is actually ruled out from the Atlas disappearing track search. But these parts, so you can see that there are still few red points are there where the relic abundance primarily governed by the annihilation contribution. Now, when a film particle is the dark matter candidate, it's very difficult to test this kind of scenario at experiments, simply because very less. Corresponding coupling is actually very tiny. So typically you don't get any signature. But here, what is happening that, so remember rho can decay to NH2, and here this Yuka coupling is actually involved. Indirectly, you can give a constraint on the dark matter mass or the film dark matter mass in this case, simply because of the reason that it's possible that if the dark matter is sub-GeV, then you can have some signal at this Mathusla. So because of this kind of decay modes, okay, so rho going to NH2. So here along the y-axis is the proton-proton 2 rho plus minus rho and rho plus rho minus production. So this is the charge PR production, and this is the associated production cross-section. Along the x-axis, it's the lifetime of this rho particle folded with this boost factor. So it's the lifetime at the left frame. These different color points, they represent the variation of the dark matter, which is the film candidate. This red line is the sensitivity reach of Mathusla. And for this kind of mass range and this kind of mixing, all the points, the scatter points, they are the theoretical prediction. So up to around 11 femtobarn is actually ruled out from disappearing track search, as we can see. So this is Atlas 13 TV. And then there are some of the points still left, which falls in this low MN region, so around the sub-GeV range, which is still accessible at the Mathusla. So the bottom line is that in this case, from the decay of NLOP, you can possibly have observable signal at Mathusla. Now this brings me to one of the slides. I have only one slide for BSM Higgs signal here, because it's very standard thing, and we have not explored this in detail, but I don't expect there will be very much new in this part. So this is for two of the, so just one minute, So the BSM Higgs, at least for the two scenarios, among the 4 scenarios, there are 2 scenarios where the BSM Higgs can be light. So we have explored that what will be the cross section. So these are, for example, the cross section for associated and pair production for 3900 TeV. And these are the sum of the branching ratio of the charged Higgs. So this is like TB bar, this is like W plus D and so on. So altogether there are Z plus mate, multi-lepton mate, and then multi-lepton multi-jet channels are possible. And this is my last slide. So because there are many late decays are involved, I mean late decays are practically in all of the scenarios playing crucial role. Where rho is underabundant dark matter, then the late decay of N compensates the relic abundance. In the second case, the late decay of rho basically gives significant contribution to the relic abundance. So one is to also take into account the constraint from Big Bang nucleosynthesis. Because if it decays too late, then it can inject sufficient amount of energy to the thermal plasma, and which will basically will be in contradiction to this BBN constraint. So all of this, so this is the lifetime of N. This is one of the scenario, and this is the hadronic energy injected considering BB bar mode. So all this part, they are basically ruled out from BBN, and these are our theoretical prediction. And as we expect that if the Yukawa coupling is very low or the mixing angle, neutral Higgs mixing angle is very low, then obviously the lifetime of N will be large and you will get severely constrained from BBN. So these things also occurs in the other scenarios, but I think I will skip this. So to summarize, this is a model that we have studied, Singlet-Triplet Fermionic model. This is a viable model for neutrino mass generation and dark matter. So in literature, there are also other versions like non-remerizable versions, which we have not discussed here. And we wanted to see that with a very nominal coupling around 10 to the power minus 10, minus 12, what kind of phenomenology is possible. And the bottom line is that with this kind of coupling, late decay contribution, this plays a significant role in determining relic abundance. And in some of the scenarios, the BSM Higgs can be accessible at colliders. And particularly if you have a sub-GeV, this film dark matter candidate, then in one of the scenario, this can be in the reach of Methuselah. So I think I will stop here. So thank you very much.
Questions? Anyone? I have one question for you, Manimala, on slide 16.
Slide 16, okay. Yes.
So you mentioned here the reach for Methuselah, right? The right one?
Yeah.
But then what are the dimensions you are using? Means what is it the full detector expected or it is some subset which is right?
So I think, I mean, they have a this technical design report, right? I mean, I don't remember exactly all the details. So I think it's written here. So this part is, we have taken from their, I mean, these are our simulation things, these scattered points. This is, we have taken from their, I think there was the design report. So we considered from there, this reach.
So if I understand correctly, you are not actually doing the simulation of Methuselah or any kind of...
No.
Okay, fine.
No, so we did the simulation for this, all these rate points, which is our theoretical prediction.
Okay, thank you. Any questions? If not, then let's thank the speaker again.
Thank you.
Thank you, Manimala.
Bye-bye.
Bye.